Okay, this is our domain of functions review. Again, another issue some of you had some concerns about, so we're going to go ahead and review it again. And I want to describe our two motivating factors when we find domain of functions. At least for right now, there's two motivating factors that cause restrictions on our domain. One is our denominator cannot be 0. And the other is expressions inside even radicals must be greater than or equal to 0. Those are the two motivating factors on restrictions on domain of functions. So when I say restrictions, I'm saying my domain is not negative infinity to infinity. If I don't see these things, if I don't see a value of x that can make my denominator 0, meaning the function doesn't have a denominator, or it's no way, even if it does have a denominator, that denominator will ever be 0, then my domain is going to be negative infinity to infinity. And if I don't see an even radical, then my domain is going to be negative infinity to infinity. So for right now, the only way I can have restrictions, I can have a domain other than negative infinity to infinity. There has to be some way my denominator can be 0, or there must be something inside an even radical that can be less than 0, because it should be greater than or equal to 0. So let's look at several cases. So we'll do several examples. These things, when you really get the hang of domain of functions, you can just look at most problems and find the answer quite instantly. So let me just write several functions and I'll write their domain. So let's say f of x, f of x is 13 over x minus 4. Let's say g of x is x squared minus 11 over x plus 1. And I was going to put a third, but it looks like my room is left out. All right. So both these functions, f and g, they don't have even radicals. So this guy is not in play, but they do have denominators. And so I have to make sure that my denominator is not equal to 0, because my denominator cannot be 0, because you can't divide by 0. You get an undefined value when you do so. So this denominator right here, well, this guy cannot be, I shouldn't solve yet, I'm sorry. This guy cannot be equal to 0, which means x cannot be equal to 4. This guy cannot be equal to 0, which means x cannot be equal to -1. Now, you know, we write these domains in interval notation, and how that works. We explained all the rationale when we went over it the first time. So this is just a quick review. So I'm just going to tell you how it works. When x cannot equal a number, it's going to go from negative infinity to that number, union that number to infinity. Negative infinity into that number, union that number into infinity. There you have the domain of those functions. Quite simple. When I say it's quite simple, I mean, you can just look at this and you can see x can't be 4. Obviously, 4 would make your denominator 0. So then you just know it's going to be negative infinity to 4, union 4 to infinity. You can just look at this guy and say x is not going to be -1. So negative infinity, -1 to infinity. It's that simple. I'll do a few more examples. However, okay, so let's say f of x is x to the 7th minus 99 x to the 6th plus 3 x to the 5th plus x squared minus 9x plus 113 over x plus 10. So again, my objective is to find the domain of this particular function. And what I know is, what I look out for when I'm finding a domain, I look for even radicals, don't see one. and I look for a denominator, which I have one. And when I see my denominator, I just have to make sure or ensure that my denominator is not equal to 0. It doesn't matter how complicated or intricate the numerator is. I need to make sure my denominator is not equal to 0. So here, x cannot be negative 10. So in interval notation, this is negative infinity to negative 10 union negative 10 to infinity. Again, I can look at this guy. I mean, these denominators can get a little more complicated, of course, than something like x plus or minus k. But when it is of the form x plus or minus k, man, I can just look at this guy. I should be able to look at this guy and go straight here. It should be instant. Look at this guy and go straight here. Okay, I'll do one more example of this type. So let's say f of x is 13 over x plus 12. So that's my function. I'm going to find a domain. At this point, you should be catching on, and you should understand the domain is going to be negative infinity to negative 12 union negative 12 to infinity. It's that simple. When you identify the value that makes your denominator 0, negative infinity to that guy, union that guy to infinity. Now, a couple of things to be careful about. Let's say f of x is 3x plus 12 over x squared plus 81. Now, in this example, my domain is negative infinity to infinity because this expression will never equal 0. It will never equal 0 because x squared will always be positive when its inputs are real numbers. So this will never, you can never take a positive number and add it to 81 and get 0. So this expression would never be 0. If you wanted to work it out, you would have x squared plus 81 is not equal to 0, which means x squared is not equal to negative 81, and you would take the square root. And you're taking the square root, which is an even root of a negative number, which you can't do, so you can't solve that. So that's negative infinity to infinity. And just one follow-up, but before I move to even radicals, if I had something like f of x is x to the 5th minus x to the 4th plus x plus 12 over 101. Well, 101 is a constant. Constants don't change. So my domain is going to be negative infinity to infinity because my denominator will never be 0 because the denominator is not changing. So the only way your denominator can become 0 is you have to have a variable in your denominator. But you've seen in the previous example that I can still have a variable in my denominator and it's still not equal 0. But the only way it can is to have a variable in your denominator. Okay, let's look at the even radical functions. So say f of x is the 8th root of x minus 3. Okay, that's an even radical. So the expression inside has to be greater than or equal to 0. So take the expression inside and set it greater than or equal to 0. Solve this guy. X is greater than or equal to 3. In interval notation, that's 3 to infinity. Again, I'm just giving a brief review, so I'm not going to go on why exactly this is, but just remember, if x is greater than some number, it's going to be that number to infinity. And it has a bracket because of the line underneath. But again, we discussed this in a little more detail previously, and we're just doing a quick review. So let's say I have another example. Let's say g of x is the square root of x plus 9. So this is the second root, the square root. We don't write the 2. That means x plus 9 has to be greater than or equal to 0, which means x must be greater than or equal to negative 9, which means my domain is negative 9 to infinity. So once again, when you get used to this, you should be able to just look at this and tell the answer. I mean, you're basically changing the sign and you know it's going to be greater than. So I should be able to just look at this. Okay, that's 3 to infinity. Oh man, that's negative 9 to infinity. For instance, f of x, this guy is the 10th root of x minus 13. That's 13 to infinity. It should be that simple. Let's say g of x is the 6th root of 12 minus x. So this one's a little bit different. But again, when you get the hang of it, even this one, you should be able to look at it and tell the answer. But I'll work this one out for you. But the procedure is the same, that 12 minus x must be greater than or equal to 0, which means negative x must be greater than or equal to negative 12. Now, what makes this problem different is this x has a minus sign in front of it, and you have to multiply or divide by -1, however you think of it, to get rid of this minus sign. And when you do so, it changes the direction of this inequality symbol. So x is going to be less than or equal to 12, which in interval notation is -infinity to 12. So really, and when you get a less than, you're -infinity to a number. So all you have to remember, if there's a minus sign, a negative sign or a negative number in front of x, it's going to end up being a less than problem because you're going to have to divide or multiply by -1, and it'll be -infinity to the number. If the x is positive, number to infinity. If the x has a minus sign, -infinity to number. Should make sense. Minus sign, -infinity. Positive x, number to positive infinity. So let me just write let me write 3 problems at once and we can go through real quick. So let's say f of x is the square root of 10 minus x. Let's say g of x is the 4th root of x plus 8. And let's say h of x is the 5th root of x minus 1. All right, so I'll write the domains right next to these. Now, again, if you have to work these out, just take the items inside where you have to and just set it greater than or equal to 0. But if you can kind of see the magic, let's just write our answers. So this guy should be -infinity to 10. This guy should be -8 to infinity. Now, a question you might ask before I get to this last example, you notice here, this guy, it was 8 here, became -8 there. And then for this one, it was 10 here, and it still stayed 10 there. Now, the reason being, this value is the value that makes this expression 0, because when we work it out, we're really setting it greater than or equal to 0. So if x is positive, it's going to be the opposite of the number to make it 0. But if there's a minus sign in front of x, then it's going to be the exact same number to make it 0. So just something to remember. And now this one, this domain is -infinity to infinity because it's an odd root. And we only have restrictions on even roots. All right, so that's going to conclude our review of domain of functions.